Hello everyone, my name is Yogesh Mishra. This video is summary presentation for the YouTube video talk with ACM A.M. awardee Dave Patterson on the topic A New Golden Age for Computer Architecture. Dave Patterson, a computer scientist and professor at the University of California, discusses the current state of computer architecture and the challenges and opportunities that lie ahead. So one of the main themes of the talk is the increasing importance of computer architecture in today's world. Patterson also argues the advance in computer architecture has played a crucial role in driving the rapid pace of technological progress and in this field that is entering a new golden age. He notes that computer architecture has become one of the most important uh, aspect than ever before as the demand of computer system has increased and the field has the potential to continue driving significant improvements in the performance and efficiency. So this in this presentation we'll cover a few topics like 50 years of computer architecture, increasing importance of our computer architecture, the shift to risk shift, the PC era to the post PC era, role of computer role of machine learning in computer architecture, the current security challenges, what are the opportunities that are there, and also risk-free system. These are the topics that are covered in the video by Dave Patterson. So starting with our first point, history of computer architecture, that is the 50 years long history covered in the video, in which IBM in 1960 came up with the issue that it was having a system that was four different machines and all were incompatible to each other. Four machines were 701, that was 7094, so 650, that was 7074, the 702, that was 7080, and 140, that was 7010 architecture, each with it having its own instruction set architectures, IO system and secondary storages like magnetic tapes, drums, and disks, each having different assembler compiler libraries with different market niches like business, scientific, or real-time implementations. To overcome that, in 1964, IBM launched IBM 360, which thought that will be like that was having one ISA system and wanted to rule the market. But with increase in technology in 1970s, that was having rapid progress in the technology, which was fulfilled by the advanced MOS technologies, imitated microprocessors and microframes ISAs. With that, in different companies started developing different products, and a few of them were Intel IAPX 432, the most ambitious microprocessor that uh, started use in 1970s. That was planned in 1970s and started use in 1975. It was a 32-bit capacity based microprocessor with object-oriented architecture, custom OS written in ADA, also with severe performance, much complexity and usability problem. The other was Intel 8086, that was 8 megahertz with 29,000 transistors. The stopgap 16-bit processor that was like 52 week to the new chip, also have ISA architecture in 3 weeks by 10% per week, assembly compatible with 8-bit 8080. The other was IBM PC 19 that was launched in the IBM PC 1981 that picked Intel 8088 for 8-bit bus, as Motorola was way more late with 68,000. Uh, the estimate PC sale was about 250,000, was which actual have became 100 million, or like overnight success. So this was some of the microprocessors that were microprocessors that were evolved. That was due to the increase in the IC technology, microcode, and CISC systems. So the logic, the RAM, and ROM all were implemented at the same time using the transistors. So semiconductor RAMs were having the same speed as of ROM. With Moore's law, memory for control store can grow. Since RAM was easier to fix microcode bugs, so it allowed more complicated ISAs, that are CISA systems, to develop. So microcomputers like Digital Equipment Corp (DEC) or VAX ISA in 1977 were developed. So while analyzing the microcoded architecture, one of the major name is John Cook Group or at IBM. So at that time, what was the plan? That hardware software interfaces will rise from assembly language to high level language programming. For that, uh, John Cook actually worked on a simple pipeline processor 801 mini computer that was that was ported to compiler IBM 370. Only used simple register and uh, load store instruction. Now there were compilers now being used as a source of measurement. The best part about 801 microprocessor, it was up to 3 times faster than the existing compiler that were used for 370 ISAs. On the other hand, Hammer and Clark at DEC in early 1980s founded VAX 1170, which was average clock cycle per instruction was 10 factorials, and found that 20% of VAX ISAs were having 60% of microcodes but only 0.2% of execution time. So covering the topic was the shift from CISC system to RISC system. As there was increase in technology, there was advancement in technology, uh, there was a shift from CISC systems to RISC systems. So to a basic comparison of CISC system to RISC system, let's take certain parameters like instruction set size and instruction format. So CISC systems have large set of instruction with variable format from 16 to 64 bit per instruction, whereas in RISC system it has a small set of instruction system with fixed 32-bit format and most register based instruction. While coming to addressing modes, there are in CISC system there are 12 to 24, whereas in RISC system there are 3 and max to 5. While talking about like general purpose registers, which in CISC there are 8 to 24 general purpose registers originally with a unified cache for instruction and data. Recent design also uses split cache, whereas in RISC system there are in a large number like 32 to 192 of GPRs are present, with most split data cache and instruction cache. Now for CPI comparison, CISC system has 2 and max to 15, whereas in RI system only one cycle for almost all instruction it has, and the average CPI is less than 1.5. While coming to the CPU control, the CISC system, which was earlier microcoded using control memory ROM, but in modern CISC system also uses hardwired control, whereas in RISC systems it had a hardwired design without control memory. So this is a basic comparison of CISC system to RISC system. While coming to the other parts, like use of RAM for instruction cache of user visible instruction was implemented. So the other topic is use of simple ISAs. So as in the advances from CISC to RISC. So instructions as simple as micro instructions were implemented, but not as wide as them. So it enabled pipeline implementation. Overall, it compiled code only using a few CISC instruction anyways. So other aspect that was at that time chosen for comparison for the performance of the processor, there was Iron's law. So in Iron's law, what it was the time per program calculation, which was equal to number of instruction per program multiplied by clock cycle per instruction and time per clock cycle. So it was observed that as the number of instruction were increased, the clock cycles were decreased in RISC system. So it came up with the output that CIC system execute fewer instruction programs, like 3 by 4 times the instruction, but more clock cycles per instruction were needed, whereas RISC was 4 times faster than the CISC system, according to the Computer Architecture Quantitative Approach book. The book is also been the author are John Hennessy and David A. Patterson. So the next topic was PC to the post PC era. So the PC era was basically the era with having the x86 transistor instruction to in the shift to internal internal RISC instructions. So the like what happened was hardware transistors uses x86 instruction into internal RISC instructions. That was compiler versus interpreter point was also there. So then you use of any RISC technique inside there was in the MPUs. Also the sale was greater than 350 millions per year. The x86 ISC eventually dominated the server as well as the desktop market, whereas within that has been ended. For the current, which is the post PC era, that is the client or cloud era, we can have an intellectual property right over SOCs. We don't need that big PCs, or we can just simply get all the things in a simple microchip. So the value died per, like, for the area, the energy being consumed, and the performance also increased. So the current sale of these systems are greater than 20 billion per year as of 2017. So 99% of these processes are currently based on this system architecture. So one of the aspect that is covered in the video is Moore's law. So first of all, we'll know what is Moore's law. It is the number of transistors on a microchip doubled every 2 years. That is the Moore's law states. The law also claimed that we can expect the speed and the capability of our computers to increase every 2 years because of this, yet we will pay less for them. So this was the Moore's law that was given, but for the current scenario, it has actually been changes, as we can see in the graph. Uh, so the blue line shows the Moore's law, the 1975 version, whereas the transistor density for the is shown in the red line, in which we can see that for the current 2020s, the Moore's law states that there is almost more than 1 million transistors needed for the calculation, whereas which is 15 times more than what is being currently used to calculate the level leaks, timing level attacks. Uh, the next topic is current security challenges. So in this topic, Dave Patterson covers the points like software are yet not secure, how you can think of the hardware, the need of is there a need of computer architecture 2.0 to prevent the timing leaks, uh, spec spectra in bugs in computer architecture definitions, etc. So in that he quotes that the new security challenges fault of the microarchitecture of the computer not only is a software, but the microarchitecture specter pointed out the time level attacks on even the hardware. So the time level attacks are greater than or even equal to 10 kb per second, that are really very high values as he quotes. So the next topic we are covering is what opportunities left in computer architecture. So this topic is being covered by Dave in first of all, first point, more software centric work for architecture. Second, the hardware centric work and their combination. So why this is so? Because as we can see in the current scenario, people are shifting to Python rather than C because of its usability in different domains. So the shift from C to Python, that is a highly interpreted language, has asked for a better architecture to work. Same as for hardware. In hardware also only this path is left, that the to develop domain specific architectures that do tasks very specific but do it very well, not like the general purpose register general purpose microprocessors that were built for working for every domain like in general, and the output was not that efficient as of this. So while talking about software centric, the modern scripting language are mostly interpreted and dynamically typed and encourages reuse, whereas it is more also this is more efficient for programmers but not for the hardware to execute. Whereas the hardware centric work, but as I said, the only path left is domain specific architectures to be developed, as being told by the most of the scientists, and just like do a few tasks but extremely well. But this will also increase again the hardware and software interface. Also, coincidentally, there are domain specific languages, not because of architectural problems, but to the efficiency of programmers and the programs and the challenges in programming to make it easy, like TensorFlow or Halide. So what if like there is a combination? So combination also will contribute again to there will be increase in hardware and software interface. So what are the opportunity in this? What are the opportunity topic? Let's have a comparison of Python and how much it is slow for the from the other options. So in this graph, it shows the matrix multiplicity speed up over naive Python for different aspects like Python, C, the parallel loop, the memory optimization, and the SIMB instruction. So from if we shift from Python to C, it shows that it is 50 times more. So the speed up is 50 times almost from Python to C, where from C to parallel loops, it again increased by 7 times. Then from parallel loops, that is parallelism, to memory optimization or using cache, it again increases to 20 times more from using parallelism to using cache memory for execution. And from memory like memory optimization used to SIMD instruction implementation, it is again 9 times. But as compared to Python to SIMD instruction, there is a 63,000 more times increase uh, for Intel, the processor 18 core Intel CPU, and SIMDs are obviously better over for check of matrix multiplicity. This graph is given by MIT. Then over if all these problems exist, then what to do? So as said earlier, so develop domain specific softwares, and like for video editing there are video editing software, for programming there are programming languages, and etc. So same as in hardware also, there will be tailored architectures that provides like the very domain specific work which it performs and perform it extremely well. So next point is not one application but one domain. So as told earlier, it's not like if a software is made for let's say example Premiere Pro, then it should work for Premiere Pro. No, it's not like that. So it is like for video editing, there should be one complete architecture that caters to all the software that are in the domain of video editing. Same as for programming or let's say gaming, there should be uh, domain specific hardware or architectural requirement. The next topic is more effective parallelism. Again, as we seen in the previous graph, so parallelism also increases the architecture efficiency for specific domain, as in SIMD is more efficient over MIMD, like the GPM, general purpose microprocessors. So again, eliminate unneeded accuracy. So for not for all softwares or not for all work, accuracy is needed. So for very specific where accuracy is needed, the architecture should have been developed for that purpose. Whereas where the same kind of accuracy is not needed, so the architecture should be that not that advanced or that low. Again, domain specific programming language will provide path for softwares. So like for example, in current scenarios for web dev, there is JavaScript being used, whereas for machine learning, Python is widely being used. So for both of them, there are different need of architecture and different need of hardware use for their work and like their use and their implementation. So what is the future? So future, David has told about his work on tensor processing unit, which is in production for 4 years, used by billions of search, which does a billions of search queries for neural machine translation for AlphaGo matches. So as mentioned by him, it is used. The chip is designed by Google for neural net interface. The feature of TPU or tensor processing unit version 1, that's a high level chip architecture. The matrix unit comprises of 65,536 8-bit multiply accumulate units, which provides a very high rate of 92,000 teraflops operation per second with a clock rate of 700 megahertz, which is needed as the work in Google is catering to a large number of calculations uh, at the same time. So the chip is 3.5 times as much on the chip memory versus the GPU. So here the GPU is actually referred to the GPU of other manufacturers, and so the other two versions of TP tensor processing unit are TPU version 2 and TPU version 3. Announced the TPU version 2 was announced 5th like the May 2017, and the TPU version 3 was announced in May 2018. With for TPU version 2, the peak performance was 11.5 petaflops per second, whereas for TPU version 3, it is announced at more than 100 petaflops per second. So here we can see that the TPU2 actually is a mm, air cooled system. So the output is not that much as of TPU v3, and at one board there are 4 TPU version 2s, whereas in TPU version 3 there are more than 4, depending on the architecture that the Google is currently being using, and it is a liquid cooled system. So there is rather more speed, like 100 petaflops per second in this system. The other companies that the other companies that has developed such neural network architectures are Google has been told earlier for TPU1 architecture with one core per chip with a large 2D multipliers and the software controlled memory instead of cache being used in Google TPU 1. Whereas in NVIDIA GPU, there are 80 cores, there are many threads like 20 MB registers, small multipliers, cache setters and getters, and code scaling hardwares. Whereas in Microsoft FPGA, it is a customized hardware, not that efficient as of Google TPU1 or NVIDIA GPUs, but is also in application. And Intel is working on its own CPU with 30 plus cores with 3 level of caches, SIMD instruction for developing this kind of neural network architectures. There is one another. There are hundreds of startups also that are being working on their own architectures and bet for better technology. Ultimately, so the marketplace again settles architecture debates. So there is this startup, Cerebus which announces an ML training chip, which was size of 300 millimeter, that is an entire wafer size of 12 inches, and the size is about 8.5 into 8.5 inch size. So this what has planned by Cerebus for ML training chip. So the next point is why domain specific architecture can win. So in this part, Dave emphasizes on the points like more effective parallelism. So more effective parallelism will again support to very specific domain. Like for a specific domain, there are specific software and hardware architectures which will be again implementing different level of parallelism. The second point is SIMD versus MIMD. So simple instruction multiple data will be more efficient than multiple instruction multiple data, which is the same as general purpose microprocessors which is being used. The next point is VLIW versus speculative or out of order. The very long instruction words will carry will get multiple instruction at the same time, whereas in compared to speculative or out of order data, much efficient use of bandwidth. So cache may work for a certain program, but not for every domain. So if we know like the memory access pattern that we can do to in the machine, and like know what is the specific very pattern, so we can use the memory more efficiently than the cache. So next topic is the RISC-V system. So the RISC-V system is still under development, and which is the RISC-V, the fifth UC Berkeley RISC, which is again is being developed at University of California, and David Patterson is the vice chairman of the RISC-V Foundation. So the key topics that tells that this architecture system may be the future of the RISC system is it is free and open. So like anyone can use it and can develop it according to their use. So like there is more competition as more innovation is again is associated in with this. So again it is independent, so you can directly pick the ISA rather than getting through a vendor which will develop it for general use. Again, it is again the future for the future is cloud, and it is for cloud and edge. So for large to tiny computers, it can be implemented. Again, the secure and trustworthiness. This is one of the most important topics because it is been an open source development. So like anyone can access it and can actually develop it according to their needs. So design your own secure course, and there is all open course, so there is no secret, so everyone can modify it according to their needs depending upon the countries on the institution that really needs that. These are simple and elegant, so as compared to earlier architecture that Gen 1 RISC 25 years later, we have learned so far that what we have learned from the first to the current RAC systems, all the vulnerabilities are overcome, and like far similar than the ARM and x86 architecture. It can add custom instructions, so it can be developed according to what a particular organization or the particular architecture needs for them. Again, input from software or architecture experts before finalizing ISA is being done. Also, the community evolves. Uh, the community for RISC-V system is being evolved, yet being evolved. There is RISC-V Foundation, owns by which owns the RISC-V ISA, and in India, under this foundation only, IIT Bombay, IIT Madras is one of the members for the research and development of RISC-V systems. So the next topic is software advances can inspire innovation. In that, actually, told by David Patterson, that the development of future hardware and hardware architecture is also based on what software is being developed. So, like in software, the next topic is software advances as inspire. So the next topic is software advances can inspire innovation. In this, like in software, like for agile development, a small team do short development between work, but incomplete prototype and get custom feedback per step. Based on that, again they reconfigure and redevelop the particular software. While using the Scrum team development also, where there are 5 to 10 people per team size, and every 2 to 4 week sprint for next prototype iteration is done, and based on that the further development is taken on. Then the new CAD enables also the software development techniques to make small teams more productive via abstraction and reuse. Same as with the agile hardware development also, like from the very basic to what the current RAC 5 systems. So there are agile developments from for each step. There are some vulnerabilities that are being sorted out in the next step. So as the same is carried out for even the current phase of development. So uh, in the end, also, the future of computer architecture that David Patterson discusses, that the likely trajectory for computer architecture in the coming years will include the likely impact of new technologies such as quantum computers and numeric computing, in which again will require different architecture, which is more scientific and research based innovation will be being taken on. So he also discusses the importance of continued research and innovation in the field, and the need of computer architect to stay up to date with the latest development. He also points, so because what currently, like software field is also growing for the same pace, the hardware field will also have to grow because of the needs of very specific hardwares in certain areas. For example, the quantum computing is there. So overall, what David Patterson in the entire talk has emphasized on the equal and the equal opportunities that are upcoming for the hardware the hardware architects is way more, and there is really a golden age because of the scenario of the change in technologies that are currently going on. So thank you very much.